Okay, let's start the Wednesday afternoon lecture. Sometimes my pace is fast, sometimes it's slow, and the weakness of the PowerPoint is everything displayed here, and all you are doing is just watching. That's very dangerous. So that's a drawback. So you have to that. I know the weakness of using PowerPoint, but you have to overcome that. So sometimes I want to really write it, even if it takes a little more time, but a lot of time it's really worth it. Okay? And another drawback of using English here in Korea, we are using Korean in our daily life. Then now the English is really second language, not the first language. So it's kind of the awkward. And usually, even if you have a question, you don't raise the question because I have to speak up in English. So that's a drawback. I said, do it using English, just do it. Raise the question, but the mind doesn't roll. So you end up not asking questions. So there are a lot of drawback. So there is a good things using English. There's a lot of weakness because of using English. But for like Augusto, if we do not use English, he can't come in the class, but you can learn Korean. And, but now Korean language is everywhere. So not just Korea. I know the Indonesian village, they are learning Korean. I saw in TV. And in grade school, elementary school, they are learning the Koreans as their second language. It's very, very good. So anyway, we'll speak up so that way we can really learn something. We talk about the stationary, we talk about the algorithmic, we talk about the non-stationary and all that sort of the processes. And for the non-stationary process, so I can write the non-stationary process as like this also, no difference. So it's exactly the same way as you wrote the stationary process, okay? No differences at all. But now you learned the basics of, you are learning the basics of the probability function. Then we can cast or explain the process using the probability a little bit here. And in any stochastic process, there is a 3 statistical parameters which you must really check whether it belongs to stationary or non-stationary or algorithmics and all that, right? So first one was what? First parameter was the mu. That's mean value, right? I'm dealing here is non-stationary process. So, which happen to be almost identical or identical notations, you can use it to explain that. This is equal to e to the x. If you use t, that's not true for non-stationary. If you use just the t, this is really the algebraic process. So I have to use this. So t1 is any arbitrarily time. So as we did before, this is x, whatever the x is, for example, gust wind speed or deformation in the motion of a plate, for example. And t, this is 0, this is x2, t, this is x1, I'll just put, and you have more. So this is ensemble. I'm just showing the family of stochastic process. You can tie to the particular type of the process, like gust wind or the pressure, okay, vice versa. So then we used we draw the straight line any arbitrarily time. So we use the t1. T1 is not just at particular time. It's really any arbitrary time. So that's what t1. You can pick up the t1 here. It's okay. So arbitrary time. So over here, RV, arbitrarily. Arbitrary, AY time. Then you can still define the mean value for non-stationary process for the given ensemble. So this is for the given ensemble. For the given ensemble. I can just use this. When you put still you can use that notation, but the t must be particular time, at any time. So in a strict sense, this I have to do. This is simply process. Okay. And what about the second parameter? Second parameter is like psi squared. This is, see, I'm forgetting myself to tell you, this is a non-stationary. I put the T, not T, T1, okay? Typical notation. And, of course, at time T1. Then, what do you call this psi square? What do you call, Chusong? What do you call this? Sungwon, what do you call this? What do you call this? This is mean square value, right? The day before yesterday, after the makeup class, on the way home, I thought, geez, all my students understood what I taught tonight. So I asked myself, and I said, maybe not. So I want to do explain and do a little more writing here. Mean square value. Mean square value. You heard about the RMS value, right? Electrical engineering expression dealing with alternate current, AC current, not the DC, AC current. Then you are dealing with the really mean square or root mean square value, RMS value. That's what this is. So this is e to the x over here, T1 square. This is expected value. Oh, here I have to write using discrete record here. Limit is 1 over n. Of course, x, I use I equal to 1 to infinity xi at T1. Pay attention on this. And in the probability sense, using that probability notation, you wrote using the probability density function. Here, I can write this guy in a sense, xi T1. If I do this, it's a little bit forcing. Some of you may not say, no, how can you do that? You could do that. You could easily do that. In a sense, I'm going to just leave this here. I'm going to just force it because for the non-stationary does not follow particular the probability density function, but I want to just show you the setup using probability function and saying that this is like 1 over n. 1 over n is something like x, px, uniform distribution function. Height here is 1 over n. Square probability density function. Strictly speaking, the expression may not be 100% true because it's non-stationary, you could say. But just assume here in this particular non-stationary process, it could be good for this ensemble. So I'm trying to force it, the forms, okay? So lots of use out there for the rectangular. This is a rectangular shape for probability density function, because area has to be 1, right? So this is so in a sense 1 over n is probability density function. Okay? N is a total number of the trier, vice versa. Then here, if I throw this into the limit n goes to infinity, n goes to infinity 1 over n. So summation I is equal to 1 to infinity xi square t1. So again, this is serving as a probability density function, as a square probability density function. What does it mean, square probability density function? Equal chance. Equal chance. Whenever you pick the experiment or trier, it occurs all the same, not like this. Equal chance. So uniform probability. This is called the uniform probability density function. So mean square value. So this is the looking at the dispersion is around x is equal to 0. Okay, mean square. So when you take square root, this is called RMS. Root mean square. Root mean square. RMS. Root mean square. So third is variance. So this is really the population statistics people, they call that as a population. It's really ensemble. Population, when you go, I saw in TV, when you go stand in Myeongdong, you know Myeongdong? Myeongdong was most busiest, crowded place in Seoul in 60s. But now it's not, right? Is it? Yun-sung, is it? Myeongdong is... When did you visit Myeongdong last time? 10 years ago? You don't go, right? I didn't go. After I came here, I used to visit Myeongdong, because that was the crowded place in Seoul. I still didn't visit. That's just bad. I should go visit. When you go visit there, there is a survey. People is doing the survey, and they put a board, big board, and they put like 3 people, like Chusong, Choru, Yunsok, and put the name here, and put the sticker, saying who is most beautiful man. Konnam? So then you're looking, this is great populations, it's less. In this case, this I-square is really, population is clustered around the 0. That's what you're looking for, to express such a thing, okay? Clustered around the 0. But variance is what? Cluster around what? Around the mean, right? So you're looking at, so when you draw the probability density function, you could use this right at 0 for the mean square, such a thing. But the variance is not. Variance is clustered around the mean value. So around here, if this is a mean, this is a mean. Okay, the variance is, this notation is what sigma we are using it. Sigma is standard deviation, but in mechanics you use the sigma as stress, right? So don't confuse this. Sigma square. If sometimes you put the x to clearly indicate the random variable, random process is x. So you could say T1. When you see this guy, it's no longer stationary. I'm sorry, it's no longer ergodic process. And this is e to the x minus, x T1 minus mu what shall I do? Mu T1 just offset, remember, just offset the mu from the x, okay? Offset. So this is equal to n goes to infinity, 1 over n. This is still the same thing, serve as a probability density function. Then summation I is equal to 1 to infinity. And what? X T1 minus mu T1. You must carry this T1. That's what I wrote there. So variance. And when you take the variance, when you take the square root of the variance, then you are talking about the sigma. So variance, take a square root. Standard deviation, I mentioned to you already, use standard deviation as a measure of quality. So quality. So remember, just for non-stationary notations are almost identical, but it's different from stationary. What's the difference between for the stationary and non-stationary? T2 and mu T1 is not equal to mu T2. For non-stationary, it's not the same. For stationary, this is the same. So that's why I bring the T1 here and T2 there. Okay. So it's worth to quickly review again. Now, this case is I talk about this all the time. Stationary process, very clear, stationary, and use of probability density notation is very clear too. Okay. This is stationary, even stationary, and I said algebraic. What does it mean? Now let's say this guy become algebraic. I think everybody understands algebraic. Someone, what's the algebraic process? Explain this. Now start from the non-stationary here. I said, what's the condition to become the algebraic process? You decided not to talk, then I better quit. Young one, can you answer? This is a non-stationary here process. To qualify, this ensemble become algebraic. What can you say? Makes sense? Question makes sense, right? Charo. I'm confused. You look like twin always sitting twin. Wear the glasses, same. But the other day you wear the cap, but only today. I forgot just what Charo. Charo, right? Yun's clear, God's clear. Charo. I have to tie with the Jeju, right? Algebraic, you have to fully understand the definition. When can you say this process is algebraic? When? Charo. One guy represents the whole ensemble of sample record. This is sample record. Each sample record, this guy represents all these statistical parameters of this guy. If that represent for the whole thing, whole ensemble, then that's the algebraic. So I want you to sit down tonight. It's so easy. And make sure what Professor Shin is talking about. And otherwise it's confusing. And homework problem number 2, you already hand in maybe up to problem 5. Then you should be very clear. When can you say ergodic? When can you say stationary? When can you say non-ergodic? And this case is, what's this case? By looking at the equation set, can you tell, oh, he's talking about the ergodic process, right? Right? How can you say that? How can you say that I'm dealing with ergodic process? Because I'm dealing with one time history, one sample record. One sample record I'm dealing with, and also I'm dealing with one sample record. And one sample record, then you can deal with probability density function, something like this. And you're dealing with the t, 1 over t, and area under is a 1. Uniform distribution, equal opportunity, then ergodic process. This simplifies everything. And one thing here is mu. Simply, I don't put even mu. Mu is a constant here. Mu is a constant for ergodic process, dealing with the one record. Represent the whole ensemble. So this is it. No more subscript 1. And the one record. So here is dealing with the one record. So mathematically, this is correct. Mathematically, this is the right expression. But t, this will never be infinite, always up to finite. Then you introduce arrow. Then you accept the arrow. So here I can write 1 over t to inside here. So this is equal to probability sense. I can say xt p x first moment. This is a 1 here. So here is this is This is 1 over t. 1 over t is here. Makes sense. So probability density function. So you can write like that. So psi square, you can tell this is here is a limit. T goes to infinity. 1 over t stays same thing. The next one gonna be 0 to t. Then x squared t dt. This is a constant, really. That's why it removed outside to outside of integration. And psi squared, the variance, identical, but x minus mu square dt, 0 to time. So if you look at inside the story, it's all fit there. So these are 3 parameters you have to remember. We're going to get some more. Okay. Yeah. So this is a special case of this. So special case. What's a special case? Mu is equal to 0. So it has a direct one-to-one relationship. I mess around with this same thing over and over again, then you will remember. Okay? And also, Gaussian distribution is what I use. I introduced only Gaussian distribution. Before end of next week, I'll introduce a few more probability density function you can use in conjunction with ocean systems engineering. Okay, and Gaussian distribution, Gaussian function, Gaussian probability function. How's this sound? Probability function. Gauss. There's a person's name, mathematician Gauss, right? Gaussian integration. Some other word is normal distribution. Absolutely normal distribution. Function. Probability density function. And if you have a chance, you can generally plot this. This is x, and this is, you can really plot this. It's not the homo. You use MATLAB all the time, right? Youngbin use MATLAB, right? Yeah, everybody's using. Other MATCAD is fine too. Then probability lowercase p, probability density function is sigma times square root of 2 pi, and 1 is e to the minus 2 sigma square x minus sigma square. This is a conjunction with the e, exponential function. And when you plot mu is equal to 0, sigma is equal to 0, then this function is called arrow function. And it shows the standardized normal density function, standardized. And you know px probability density function is integration from 0 to the x px dx, right? So this is, if I put this guy is something like this, integration means, okay, from 0 to up to x. Integrate means just to compute the area under. But this Gaussian density function or the normal density function, if you keep extend, it never touch. Here at the end here, never touch. Okay. So in a strict sense, any physical phenomena, you cannot use this Gaussian probability density model. Why? Because here, never touch. It can really approach to the other side, the other line, but never touch. So all the physics, it touches. So, but it's okay. We can live with a few percent error, isn't it? That's the beauty. Engineering, we can live, no problem at all. That's why we use Gaussian distribution all the time. Okay? That's what you're using it. But here, by looking at this, the probability, Gaussian probability distribution function is integration. Let's look at this a little bit here. So I'm going to put it here. Before I put it here, I'm going to before I put it here, square root of 2 pi and sigma, okay, 1, e to the minus 2 minus 1/2 sigma x minus mu squared. The same arrow function. I'm going to do this, let's say the z, replace this guy as a z parameter. If I do that, this guy will be, it's simply px, okay? If you do that, then this is 2 pi sigma e to the minus 2. Minus 2, and this guy is a z, right? Then now we have to, I want to do integration from 0 to x to get the p. X. But this is a z. So now I'm just looking at this dx. But this dx, this is a z, so z is equal to sigma x minus g. I want to take differentiation, which is equal to sigma 1. This is it. Right? Just do the differentiation. So then I can write as dx is sigma dg. I'm going to plug right here. I'm going to plug this right here as sigma dg. And sigma cancels up. Then now this is integration. This is integration of 1 over 2 pi e to the minus half z square dg. So now this is now integration is with respect to z, not the theta. And limit is x, so we have to put the proper x. So now z is this. So integration should be up to the z. But here is up to the x. So this is integration is up to here. So I have to put the x. You have the corresponding parameter limit is z. So I'm going to say simply just z. So this function, arrow function, is called the arrow function, or standardized Gaussian density function. So it's all tied into there. Okay, most popular. So most popular density function you should know in and out, which I didn't. The last thing is plot. You can plot it. Plot it, and show me Friday. I want to make sure you plot. And then increase. This is 0. Then it's gonna be center gonna be line up on the y-axis, p-axis. Then sigma keep increase. Higher. Then what do you expect? If theta is very small, what do you expect? You expect that this guy is going to be really go like that. And sigma goes really small, it's going to, right? Quality is bad, vice versa. So please do that. Oh, this is over here. Okay, there is a central limit theorem. I just show you this theorem. There are lots of situations you have like x1 random process follow something like a normal, but x2 follow different distribution, x3 follow different distribution. Then my question is, what happened when x1 plus x2 plus x3, for example, this is, let's say, x. If this follows normal, if this follows normal, surely x follows the normal distribution. So it is without proof. It's all okay, it's good. But if this follow normal, if this follow log normal, If this follow normal, the result variable, what does it follow? In terms of the probability function, it's not log, it's not normal, something else. Okay, so that's a dilemma. Then one person who is a Pearson, he wrote a paper some years ago, I forgot what year. He wrote a paper saying that he identified a few different parameters and saying that for this case it follows this type of, for this case it follows another, for this case, so it isn't popular, but in 60s it was popular. So but if random variable process is many, all different kind of the probability density function it follows, if there are a lot of parameters, it has a tendency that resulting variable follow the normal distribution. That's what this is saying. I'm gonna keep talking Friday from this and move on. And I want you to read also the chapter 2A, which is a joint probability function. You have I'm pretty sure you have a copy. Check it out. You have a copy? 2A, right? 2A. So review the joint probability distribution function. Review that. Okay, I'll stop right here.